In this video, I will show you how to solve exponential and logarithmic equations. This is AP Precalculus topic 2.13. If you appreciate this content, please give it a like. Example 1, Part A. When there is only one exponential term, the first step is to isolate that term. So in this case, we can subtract 5 from both sides, which will leave us with 2 to the x plus 3 power is equal to 21. There are two ways to think about what's going to happen next. One way to think about it is that we are switching forms from exponential form to logarithmic form. In a previous lesson, we learned that if we have the exponential form b to the c power is equal to a, we can rewrite this in logarithmic form, which always begins log base. Here the base is b, so we will begin with log base b, writing that base as a subscript. The other two numbers, variables, switch sides of the equation. So the a ends up over here on the left, and the c ends up over here on the right. So back to this equation. If we change from exponential form to logarithmic form in this exact same way, we can begin by writing log and base 2 as a subscript. Now the 21 and the x plus 3 will switch sides of the equation. So the 21 will end up over here, and the x plus 3 will end up over here. So that's one way to think about it. Another way to think about it is that a log base 2 will cancel out this base 2. So we can solve this equation by taking the log base 2 of both sides of this equation. On the left side, the log base 2 and the base 2 will cancel each other out, and x plus 3 will be left behind. So we get x plus 3 is equal to log base 2 of 21. And this is the same equation that we got by the first method. To finish the problem off, we will get x by itself by subtracting 3 from both sides. So that will leave us with x is equal to log base 2 of 21 minus 3. And this is the answer in exact form. We could put this into the calculator and get a decimal if this was on a calculator active part of a test. Example 1, Part B. Let's begin by trying to isolate the exponential term. Subtracting 3 from both sides of the equation gives us negative 10 is equal to negative 4e to the x power. We need to get e to the x power by itself, so let's divide both sides by 4. So that would leave us with positive 10 over 4 is equal to e to the x. This will reduce down to 5 over 2. We can cancel out this base e with a log base e, but instead of writing log base e, let's take the natural log of both sides of the equation. This means the log base e of e, so these will cancel each other out. Next, we are left with the natural log of 5 over 2 on the left is equal to x. And that's the answer. Example 2, Part A. When you have a log equation with only one log term, the first step is to isolate the log term. So let's subtract 4 from both sides. That will give us 2 times the log base 3 of x plus 3 is equal to 6. Dividing both sides of the equation by 2, we get log base 3 of x plus 3 is equal to 3. There are two ways to think about what I'm going to do next. One way to think about it is that I'm going to change from log form to exponential form. In exponential form, you start with a base, but there will be no log. So I'm going to take this base b and I'm going to just write that down. Now the a and the c switch sides of the equation. So the a comes over to the left and becomes the exponent, and the c goes over to the right. So log form becomes exponential form. These mean the exact same thing. If I apply this reasoning to this equation, then I will bring down the base 3 that's right here. And then the x plus 3 and the 3 will switch sides of the equation. So we will get 3 to the 3 power is equal to x plus 3. Another way to think about it is we can cancel out a log base 3 with a base 3. So let's drop a base 3 on both sides of this equation. It's called exponentiating both sides of the equation. The base 3 and the log base 3 cancel each other out. So on the left side, we are left with x plus 3. On the right side, we have 3 to the 3rd power, which is 27. This is the same thing we would have gotten from the first method. Continuing on, let's subtract 3 from both sides, and we get x is equal to 24. So that's the answer. Example 2, part B. Let's try to isolate the natural log of 2 minus x. Let's start by multiplying 5 on both sides, so that will give us the natural log of 2 minus x is equal to 5. Now, remember, this is really log base e of 2 minus x. So we can cancel out the natural log with a base e. So let's exponentiate both sides of the equation by dropping a base e on both sides. On the left side, the e and the natural log will cancel each other out, leaving behind 2 minus x. So now we have 2 minus x is equal to e to the 5th power. Subtracting e to the 5th power from both sides and simultaneously adding x to both sides, we will get 2 minus e to the 5th power is equal to x. And we've solved it. When you have an equation with more than one log in it, you can usually simplify it down to either form 1, where you have one log, or form 2, where you have a log equal to another log. If you simplify it down to form 1, we can solve it like we did on the previous examples. Like in this case, we would drop a base a on both sides of the equation. If you simplify it down to form 2, you can finish solving by setting the x part equal to the y part. So here's 2 important notes. Number 1, we have to be careful to check for extraneous solutions. Sometimes log properties can lead to some solutions that are not actually in the domain of the original problem. For example, you cannot take the logarithm of 0 or any negative number. So you have to make sure we're not getting any zeros or negative numbers on the inside here. Also, notice that the log x plus the log of y equals the log of z does not simplify down to x plus y equals z. You have to use log properties to simplify this down and solve. Example 3, part A. We have learned that the sum of 2 logs can be written as the single log of a product. So the log of 3 plus the log of x plus 4 can be written as the single log of 3 times x plus 4. Let us go ahead and distribute this. 3 times x plus 4 is 3x plus 12. The part on the inside of the function is called the argument. When you have a log equal to another log, the argument must equal the other argument. So 3x plus 12 must equal 5x minus 2. So this is algebra 1. Subtracting 3x from both sides gives us 12 is equal to 2x minus 2. Adding 2 to both sides gives us 14 is equal to 2x. And dividing both sides by 2, we get 7 is equal to x. Now that is probably the solution, but we need to check for extraneous solutions. Remember that you cannot take the log of 0 or a negative number. So we need to make sure that plugging this back in will not give us any negative numbers or a 0. Plugging 7 in right here gives us 11, so that's fine. Plugging 7 in right here, that's 35 minus 2, so that's 33. That's also fine. So this is fine. Part B. We have learned that the difference of two logs can be written as the single log of a quotient. So we can rewrite this as the natural log of x plus 1 over 3x minus 5 is equal to the natural log of 7. Now that we have a log equal to another log, the argument inside must equal the other argument. So x plus 1 over 3x minus 5 must equal 7. Multiplying both sides of the equation by 3x minus 5 is going to leave us with x plus 1 is equal to 7 times 3x minus 5. Distributing the 7, we have x plus 1 is equal to 21x minus 35. Subtracting x from both sides, we have 1 is equal to 20x minus 35. And adding 35 to both sides, we get 36 is equal to 20x. Dividing both sides by 20, we get 36 over 20 is equal to x. Reducing, dividing the numerator and the denominator by 4, we get x equals 9/5. Part C. The sum of two logs can be written as the single log of a product. So we can do x plus 2 times x minus 3. This will have to be FOILed out. So we have the log base 3 of x squared. Outer, I have negative 3x. Inner, I have positive 2x. So that's going to end up with negative x in the middle. And then 2 times negative 3 is negative 6. So that's what you get when you multiply these two together. And this is equal to the log base 3 of 14. Now that we have a log equal to a log, the argument will equal the other argument. So x squared minus x minus 6 must equal 14. Subtracting 14 from both sides gives us x squared minus x minus 20 is equal to 0. I bet this is factorable, so let's go for it. X squared can only be factored as x times x. 20 can either be factored as 4 times 5, or 2 times 10, or 1 times 20, but I think it's going to be the 4 times 5 that we need. So let's do 4 times 5. Inner plus outer must equal middle. The middle is a negative 1. So inner I have 4x, outer I have 5x. To get a middle of negative 1, I need a positive 4x and a negative 5x. So I will put the positive here and the negative here. Also, positive 4 times negative 5 is negative 20. Using the zero product property and setting each one of these factors equal to 0, we get x is equal to negative 4 and x is equal to positive 5. Let's be very careful and make sure that neither of these solutions are extraneous. If we plug negative 4 in right here, that's negative 4 plus 2, that's negative 2. You cannot take the log of a negative number. So we say that the solution x equals negative 4 is actually extraneous. So we have to eliminate that from the options. Plugging in a 5 does not cause a negative number or a 0. 5 plus 2 is 7, 5 minus 3 is positive 2, so this one is good. That's why x equals 5 is the only answer. Example 4, part A, has this extra step to it. We need to move this 3 to the exponent of the 2 before we can combine these into a single log. So I'm going to move the 3 right here and make it 2 to the 3rd power. So on the next step, I'm going to have the log base 4 of x minus the log base 4 of 8. 2 to the 3rd power is 8. And this will equal the log base 4 of x plus 7. Now we can combine the difference of two logs into the single log of a quotient. So this will be the log base 4 of x divided by 8. And this will all equal the log base 4 of x plus 7. Now that we have a log equal to a log, the arguments must equal each other. So x over 8 must equal x plus 7. Multiplying both sides by 8, we get x is equal to 8 times x plus 7. That means x is equal to 8x plus 56. Subtracting 8x from both sides, we get negative 7x is equal to 56. And dividing both sides by negative 7, we get x is equal to negative 8. And that's the answer. Well, wait. This could be extraneous. So if we plug negative 8 back in, let's say right here, that's negative 8 plus 7, which is negative 1. We cannot take the log of a negative number, so this solution is extraneous. Because our only solution is extraneous, that means that this log equation has no solution. So that is the answer. Example 4, part B. We need to rewrite this equation so that both log terms are on the same side of the equation so that we can eventually combine them into a single log. So I'm going to bring down my log x, and let's subtract log of x minus 7 from both sides of the equation. In other words, let's move this log term over to the left, and we will have minus the log of x minus 7. Simultaneously, let us add the 2 to both sides of the equation. So let's move this 2 kind of over to the right, and it will be a positive 2 now. We know that the difference of two logs can be written as the single log of a quotient. So we will have the log of x over x minus 7 is equal to 2. Since this is a single log involved in this equation, we can exponentiate both sides to solve this. The base is invisible, so it must be a 10. So we can solve this by dropping a base 10 on both sides of the equation, like this. Base 10 and log base 10 cancel each other out. So on the next step, we will have x over x minus 7 is equal to 10 squared, which is 100. Multiplying both sides by x minus 7 will give us x equals 100 times x minus 7. So we have x is equal to 100x minus 700. Let's simultaneously add 700 both sides and subtract x from both sides. So we will now have 700 over on the left because we added 700 to both sides. Subtracting x from both sides will leave us with 99x. Dividing both sides by 99, we have 700 over 99 is equal to x. As long as this is not extraneous, this is going to be the answer. Notice that 700 divided by 100 is 7. So 700 divided by 99 is a little bit bigger than 7. That's important because if I plug it in right here, this is a number that is a little bit bigger than 7 minus 7. So this will be a positive number. And obviously this is a positive number, which works right here. So that's how we know that this value is okay. It is not extraneous. Example 5. Let f of x equal the natural log of x plus 15 minus the natural log of x, and let g of x equal the natural log of x plus 3. Find all values of x where the graphs of f and g intersect. The intersection points will be the values of x where f of x equals g of x. So let's set f of x equal to g of x and solve. We know that the difference of two logs can be written as the single log of a quotient, x plus 15 over x. Now that we have a log equal to another log, the arguments on the inside must be equal. So x plus 15 over x must equal x plus 3. Multiplying both sides of the equation by x, we get x plus 15 is equal to x times x plus 3. I'm going to go ahead and put x squared plus 3x. I'm distributing the x as I multiply. Let's get 0 on one side. So subtracting x from both sides, I'm going to have x squared plus 2x. And then subtracting 15 from both sides, we have minus 15. Hopefully this is factorable. Otherwise, we will have to use the quadratic formula. But let's try factoring first. X squared will only factor as x times x. 15 will factor as 3 times 5, and 15 times 1. Inner plus outer must equal the middle. Inner, we have 3x. Outer, we have 5x. To get a middle of positive 2x, we need a negative 3x and a positive 5x. So negative here, positive here. Also, negative 3 times positive 5 is negative 15. So this is working. Using the zero product property and setting each of these factors equal to 0, we get x is equal to 3 and x is equal to negative 5. We just have to check and see if any of these are extraneous. Let's start with negative 5 because it looks the most suspect. If I take x equals negative 5 and I plug it in right here, well, that immediately gives us the log of a negative number, which is not allowed. So x equals negative 5 is an extraneous solution. That one is out. How about the 3? 3 itself is positive, so that's going to be fine right here. 3 plus 3 is 6, that's fine. 3 plus 15 is 18, also fine. So x equals 3 is the only solution. Example 6. Let h of x equal this log expression, and let k of x equal this log expression. In the xy plane, what are all x coordinates of the points of intersection of the graphs of h and k? The intersection points will be the x values where h of x is equal to k of x. So, as before, our strategy will be, let's set these two expressions equal to each other and solve. We begin with this, but we know that the sum of two logs can be rewritten as the single log of a product. So the log base 3 of 2x minus 3 times x plus 4. And this will equal the log base 3 of 8x plus 2. Let's FOIL this out. So we will have the log base 3 of 2x times x is 2x squared. Outer, that's 8x, minus an inner of 3x, so that's going to be 5x in the middle. And then negative 3 times 4 is negative 12. And this will equal the log base 3 of 8x plus 2. Now that we have a log equal to a log, the argument must equal the other argument. So 2x squared plus 5x minus 12 must equal 8x plus 2. Let us get 0 on one side. So I'm going to bring down my 2x squared, but let's subtract 8x from both sides. So that will give us a negative 3x on the left. And let's subtract 2 from both sides. So we will have minus 14 on the left. Equals 0. Hopefully this will factor, because I really do not feel like doing the quadratic formula today. But hey, if we have to do it, we have to do it. The first term will only factor as 2x times x. 14 is either going to factor as 2 times 7 or 1 times 14. Let's start with the 2 times 7. So either I'm going to put a 2 here and a 7 here, or the other way around. Here's a little shortcut. If there was no common factor in the original trinomial, there will be no common factor in either set of parentheses. So I know the 2 cannot go here because that leaves a common factor of 2. So I won't even waste my time thinking about putting it in that order. I'm going to go straight for 7 and 2. And if this doesn't work, I'll know it has to be 1 and 14 instead. Be careful, some students get confused when there's an actual number out in the front. Notice that we cannot look at the 2 and 7 and immediately look for a 3. Instead, we use the mantra inner plus outer must equal middle. Inner, we have 7x. Outer, it's the product of these two, that's 4x. And it is these that we must use to make a middle of negative 3. To form a negative 3x, we need a negative 7x and a positive 4x. That means the negative goes here for the negative 7, and the positive goes here for the positive 4x. Also, notice that negative 7 times positive 2 does give us negative 14. Using the zero product property, in other words, setting each of these factors equal to 0, we get x is equal to 7 over 2, and x is equal to negative 2. But we must be careful to make sure that neither of these answers are extraneous. Let's start with x equals negative 2. So if we were to plug negative 2 in right here, that would make 2 times negative 2, that's negative 4, minus 3, that's negative 7. You cannot take the log of a negative number, so this solution is extraneous. Get it out of there. If you were to plug in 7 halves right here, so 2 times 7 is 14, divided by 2 is 7, minus 3 is 4, that's going to be okay. Plugging in a positive number here is going to give us a positive number because it's all addition. Same here. Plugging in 7 over 2 here, and this is all addition, it's going to be positive. So x equals 7 over 2 is the only solution. Example 7. In order to solve an equation that involves multiple exponential functions, it's important to get like bases. So for part A, we already have like bases, so this one will be very easy. If the bases are equal, then the exponents are going to have to be equal as well. So that means that 5x minus 1 must immediately equal 2x plus 7. And we're back to algebra 1. Subtracting 2x from both sides gives us 3x minus 1 is equal to 7. And adding 1 to both sides gives us 3x is equal to 8. Which means that x is equal to 8 over 3 when we divide both sides of the equation by 3. For part B, we start with two different bases, but no worries, we can write both of these expressions with a base of 2, because 8 can be written as 2 to the third power. The extra exponent of 3x minus 2 goes right here. So 8 to the 3x minus 2 power becomes 2 to the 3 times 3x minus 2 power. And this is equal to 2 to the x plus 5 power. Now that the bases are equal, the exponents must be equal. So I'm going to set these equal to each other now. But as I do it, I'm going to distribute this 3. So I'm going to get 9x minus 6 is equal to x plus 5. Subtracting x from both sides, we get 8x minus 6 is equal to 5. Adding 6 to both sides, we have 8x is equal to 11. And dividing both sides by 8 gives us x equals 11 over 8. So that's the answer. For part C, on the left we start off with a base of 1/2, and on the right we begin with a base of 4. Luckily, both of these can be rewritten as a base 2. 1/2 can be rewritten as 2 to the negative 1 power. And then we take the 5x plus 7 and we multiply in the exponent, like this. 4, of course, can be written as 2 to the second power. And then the x gets multiplied right here. Now that we have like bases, we can set the exponents equal to each other. Distributing this 1, we will have negative 5x minus 7 is equal to 2x. Adding 5x to both sides will give us negative 7 is equal to 7x. Dividing both sides by 7 will give us negative 1 is equal to x. So that is the solution. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.